We've all come across those familiar illustrations of the solar system in schoolbooks, the sun appearing just a bit bigger than Jupiter. But that depiction doesn't do justice to the actual proportions. The sun is so immense, it could contain around 1,000 Jupiters within its volume. As awe-inspiring as that sounds, our sun isn't the largest star known, not even within our own galaxy. That distinction belongs to Astronomy, and in comparison, our sun is like a minuscule grain of sand, but the story gets even more astonishing. Researchers have recently discovered something far more perplexing and ancient: mysterious star harboring a black hole at its core. It is a cosmic enigma that not only confounds astrophysicists, but could also shed light on the origin of the universe as we know it. But how can a black hole possibly exist within a star? Why were these stars so unimaginably large? And what would occur if a black hole star drifted into our solar system? Stars are like the universe's forges. Within their blazing cores, they manufacture most of the elements we find throughout the cosmos. But the celestial bodies that may have existed in the infancy of the universe were unlike the stars we see today. Rather than traditional fusion-powered centers, they concealed black holes within, enabling them to expand to truly incomprehensible dimensions. Ordinary stars originate from massive clouds of interstellar gas and dust, where gravity pulls the densest regions together. This collapsing matter heats up, forming what's called a protostar, the initial phase in a star's development. As the core temperature rises, the protostar gathers more material from its rotating disk until it finally ignites nuclear fusion, transforming into a main sequence star. For our sun, this transformation took approximately 50 million years. Most stars spend the bulk of their lives in this stable phase, steadily converting hydrogen into helium. Eventually, however, all stars meet their end, either fading into white dwarfs if they lack sufficient mass, or exploding in supernovae if they are massive enough. After such an explosion, the stellar remnant may become a neutron star or collapse into a black hole, depending on its original mass. In about 5 billion years, when our sun exhausts its hydrogen, it will balloon into a red giant, growing 200 times larger before eventually shedding its outer layers and leaving behind a white dwarf. This incredibly dense object, nearly 200,000 times heavier than Earth yet similar in size, will gradually cool from 10 million degrees Celsius 18 million F. Over the course of around 10 billion years, the white dwarf will crystallize, much like how water transitions into ice, though in this case, it will be a lattice of carbon and oxygen atoms. For stars more than 10 times as massive as the Sun, a different destiny awaits. They are large enough for their cores to collapse following a supernova, but they might still not be massive enough to form black holes. So what becomes of them? Within these colossal stars, the intense gravitational pressure crushed electrons and protons together, forming neutrons. Because neutrons resist further compression, they stabilize the star into a new form, a neutron star. These stellar remnants are the densest known entities besides black holes. Roughly the diameter of a city, around 12 miles or 20 kilometers, a neutron star still holds a mass comparable to the Sun. On Earth, a mere sugar cube-sized piece of neutron star matter would weigh about 1 billion tons, roughly the mass of a mountain. So how exactly does a star evolve into a black hole? While the star is still active, two opposing forces maintain a delicate balance: nuclear fusion pushing outward and gravitational force pulling inward. Once the fusion process ceases, gravity overwhelms the structure, and the star collapses inward like a demolished skyscraper. Einstein theorized that any object, if compressed into a small enough space with sufficient mass, could form a black hole. These gravitational giants continue to expand over time, swallowing anything that ventures too close. As the region around them, called the event horizon, grows, so does their appetite for nearby material. You might compare this to a sinkhole expanding beneath collapsing terrain, but instead of soil, it's gravity warping spacetime. Typically, black holes have a restriction on how rapidly they can grow, thanks to a phenomenon called the Eddington luminosity limit. It's akin to inflating a tire. Once pressure builds, the air escapes through tiny leaks, preventing overextension. Similarly, the intense radiation generated near black holes pushes some infalling matter away. As material spirals into the black hole, it accelerates, and up to 42% of its mass can be transformed into radiant energy. This energy is so potent, it actually exceeds what stars produce via nuclear fusion. Just imagine the potential if we could somehow harness this force as a power source. Even the gargantuan black holes at the centers of galaxies, supermassive black holes, adhere to this limit. However, some of them appear to be far larger than current formation theories can explain. This conundrum is one of astrophysics' greatest unresolved puzzles. Enter quasi-stars, or black hole stars, hypothetical titans that may have been the most massive celestial bodies to ever exist. They may have dwarfed even the most colossal black holes we've discovered so far. In the current universe, the conditions necessary for their formation no longer exist. But in the cosmos' earliest epochs, the universe was teeming with enormous clouds of primordial gas. Gravity compressed this material into behemoth protostars. There's even a theory that these giant stars emerged from invisible dark matter halos, with masses up to 100 million times that of the Sun, serving as cosmic cradles for these monsters. Usually, massive stars explode violently in supernovae, leaving black holes in their wake. But these titans were so vast that they absorbed the explosion's shockwave instead of dispersing. Rather than exploding outward, their cores collapsed inward into black holes, while their outer layers remained intact. If you were close enough to witness it, you might not even perceive a change, at least not right away. But now, the newborn black hole begins devouring its stellar host from the inside out. Spinning rapidly, it forms a scorching accretion disk around itself, where matter spins at nearly light speed. Because the star's internal pressure funnels gas directly into the black hole, it consumes material at a furious rate. This friction heats the disk further, radiating energy so intensely that the quasi-star could outshine entire galaxies. These monstrous objects may have grown faster than any black hole we've ever studied. In just a few million years, some exceeded even the largest known stars like Stephenson 2218, UY Scuti, or the black hole Ton 618. They might have expanded to be thousands of times larger than the Sun, possibly as wide as our entire solar system. But such an enormous size also meant a shorter life. While the Sun will endure for billions of years, quasi-stars lived fast and perished young, eventually erupting in spectacular fashion, releasing ravenous black holes into space. But what if one of these monstrous stars entered our solar neighborhood? Its gravity would destabilize planetary orbits, hurling asteroids toward Earth and dragging planets off course. Long before it reached us, the radiation and heat would render Earth uninhabitable. Eventually, it would engulf our planet, though humanity would be long gone by then. Some scientists suggest that these early quasi-stars seeded the supermassive black holes found at galactic centers. Their interactions with surrounding matter may have generated gravitational waves that influenced how galaxies formed and where stars settled within them. These exotic stars might have even affected the potential for life. Their intense radiation could have sterilized nearby planets or shaped prebiotic chemistry in unexpected ways. In the grand narrative of cosmic evolution, quasi-stars may have sculpted the universe's earliest architecture. Here's another mind-bending idea. Although none likely exist now, miniature black holes from the dawn of time might still be roaming the cosmos. If numerous enough, some could have ended up trapped inside star-forming gas clouds. Eventually, as new stars formed, these ancient black holes could settle into their centers. Even a black hole with Pluto's mass could balloon to an enormous size in just a few 100 million years. It's conceivable, though unlikely, that our own Sun harbors one. Stephen Hawking once proposed this intriguing possibility. If such a black hole had the mass of Mercury, we might not even detect it. However, astronomers are working on ways to identify such hidden black holes. One approach involves studying unusual red giant stars. Those containing black holes might be slightly cooler than expected. Already, about 500 anomalously cool red giants have been observed. By analyzing their oscillations' subtle starquakes, if you will, scientists hope to determine if they harbor primordial black holes. And here as the final twist, some experts believe dark matter itself might be an ocean of these miniature black holes, swarming invisibly through the cosmos. If so, then at least a few could have become embedded inside stars. We'll need to wait for science to provide the answers, but until then, stay curious. Don't forget to share your thoughts about quasi-stars in the comments. We read them all. Thanks for tuning in, and keep watching for more breathtaking cosmic revelations.